So I have a question. I want to know if there's a term you ever heard before. Suppose you're sitting there. Let's pretend COVID isn't happening or whatever. You got a buddy. They own a hot dog stand downtown. You're curious, so you say to him, how do you do on that hot dog stand on a Saturday night? How are things go? And your friend says, well, my net profit last Saturday was $400. Taxes, that has something to do with it, but what else might be expenses in a hot dog cart other than taxes? Right, yeah. So when he says his net profit is $400, now taxes, there's your personal income tax. That's a whole different story. But let's say he has $1,000 in his till at the end of the Saturday night. Well, he's got to pay for the hot dogs. He does have to pay sales tax to the government. He's got to, there's the licensing and so on and various other things. So his net is what's left over after everything all is said and done. And of course, as a business person, what you want is your net not to be negative. He could have $200 in his pocket at the end of the night, but actually have lost money when you factor in all the various things. So we are going to talk about this in the context of chemical reactions. And as I said, this is the last piece that we need to look at. So there are these things that are called complete ionic equations, and I'll show you an example of one, what they are in a minute. But they're the equivalent, sort of when your friend at the till at the end of the Saturday night, he's got $1,000 in there, but it doesn't mean that that's all money that is kept. You have to consider other things. So what we call complete ionic equations are going to express all reactants and products in their true ionized form. We were talking, I think it was last class, we were drawing those little beaker diagrams, and we were talking about how ionic compounds, they break apart into these ions in solution. I talked about it a bit on that video also that you were supposed to have watched before last class. So here we have a chemical equation. And in just a second, I'm going to what I should say is this. This is the way we write chemical equations. We write them this way for a number of good reasons, for convenience, and to do some things we're going to do in the unit after this. We write them this way. It makes it easier. But we also need to understand as chemists that actually it's a little bit more complicated because these aqueous things, these are actually broken apart, and I'll show you what I mean by that in a moment. So I'm going to switch over here to my notepad. Oh, I'm going to pause it for a second. So if you were here last class and you remember, I did basically this exact reaction. I had two beakers and I poured them into one. And so this is what I'm going to do on these little reaction beakers. This is supposed to be a beaker. And here's another one. So I've got a beaker for each of my reactants. And then I'm pouring those beakers together into the same beaker. And a chemical reaction does happen, and I can tell because I'm producing a solid, which is necessary in double replacement. So, as I said, we've written it this way, but really, these calciums and these chlorines are not attached to each other. And as we were talking about last week, they're going to break apart. They're going to what we call ionize in solution and just be floating around in invisible, separate calcium ions and chloride ions. Same thing with this sodium carbonate is going to be broken up into sodium ions, two of them, plus a carbonate. And so I take those and I pour them into the same beaker, and when I do that, calcium carbonate is not soluble. It does not dissolve in water. So what I'm saying is that it doesn't ionize like that. By the very fact I'm saying it's not soluble, by the very fact I'm saying it's a solid, it's not doing this stuff that the others are doing. However, there is this dissolved sodium, and notice there's a coefficient 2 there. So there's 2 sodiums, and there's 2 chlorines, 2 chloride ions. And so this is sort of the kind of the before and after of my chemical reaction. So I think I said full ionic, complete ionic, same thing. And we won't write too many of these complete ionics because they're kind of a pain. But it would look like this. I'm basically just writing out the ions that I have and the number of them that I have. And again, notice I'm not breaking up the calcium carbonate by the very fact that it's a solid, it's not dissolved. So your solid one is not going to be ionized. So after this, we're going to write the net ionic. But there's a couple things that I want to point out here. Number one, so if you think about, like, for example, these sodium ions right here. So this is like the before, over here on the left. This is the before, and this is the after on the right. Before the reaction, there were 2 sodium ions floating around in the water, and after the reaction, there's 2 sodium ions floating around in the water. Same thing with these chloride ions. 2 ions floating on the water before and after. So actually, absolutely nothing happened to those. Nothing. They just are sitting there in the water, floating around just like they were before. Now, something happened to the calcium and the carbonate. They joined together in this new substance, calcium carbonate. It wasn't there before. So what we're going to do in the net ionic is eliminate the things that actually didn't react. Before I do that, though, I want to comment on the way that I wrote this and why it's not. Some of you might be thinking, why didn't you do that? You're always saying chlorine's diatomic and so on. You should put a subscript 2 there for the element chlorine. It's part of Bringelhoff. Well, here's the thing. This is not the element chlorine. The element chlorine is a gas, okay? If I have the pure element chlorine, it is Cl2. It's a poisonous gas. If I had some of it in here and I let it out in this room, we would all die. We would inhale it. It turns to hydrochloric acid in your lungs, and you die a horrible death, just like the people in World War I when this was literally used as a chemical weapon. Chloride ions, on the other hand, which is what is here, are totally different, totally safe. They're in your food. If there's any salt in your food at all, there's chloride ions in your food in all kinds of places, so they're fine. So the fact that this is negative and the fact that it has a -1 charge is important. And no, in this situation, we're not going to write a subscript 2 there. So we should write it just how I have it. Questions about that? So if you look at the net ionic, we could figure it out a couple different ways. But if you look on each side of my equation here, I've got things that are like exactly the same. These. And these, the chloride ions, as we just mentioned. So my net ionic is just going to, kind of like I was talking about with the hot dog stand, we're going to eliminate all the extraneous stuff, the extra stuff, and just write what's left, which is this. The charges are important. They have to be there. An ion is a charged thing, so you leave these charges off, I'm going to count it wrong. So basically, this entire reaction, all of this stuff can be boiled down to this last thing right here. This is the only thing that's really actually happening. A calcium ion is making a carbon-diene and forming. Go ahead. Exactly. It's just the things from the insoluble part. Yep. Other questions about that? So as we've been talking about, and I was just mentioning, like in that last example, the sodium ions and the chloride ions don't do anything in that last example. So, they're called spectator ions. They're like a spectator at a sporting event. They're just on the sidelines, not doing anything, not actually involved. Truly nothing is happening to them. And so to be a spectator ion, nothing can change. Now, this second bullet, for the types of net ionics that we're going to write, it's probably not as important. But if something's going to be a spectator ion, nothing can change about it. So it can't go from aqueous to solid. Nothing at all can change about it. So it's going to be aqueous on both sides, same charge on both sides. Again, in these reactions, we're going to look at the charge isn't going to change, but and so a spectator ion just doesn't have a spectator ion just doesn't have the a net ionic equation doesn't have the spectator ions. All right. Let's look at another one. Okay, so we'll do the same thing we did last time, except we're going to write those beakers, and then we are going to write the net ionic equation. All right. So there's my beaker. That's supposed to be a beaker with water in it. Another beaker with water in it. And we just have one for the products because we're pouring the two beakers together, and they're maybe doing a chemical reaction. Yeah, sorry if that's hard to see. CO3, calcium nitrate. Let's see if I can make it a little bigger. Move this around. All right. I left the lid. Or the rim, I should say. Okay. So, here we have all these things that are aqueous are actually ionized. Ag plus, a little bit better. Ag plus, and I'm drawing two of them because of the coefficient 2, and it's also just going to keep things balanced. That's a 3. It doesn't matter where you draw these in the beaker. I'm just, as long as they have their charges on them. And then we got a calcium ion, which is positive 2, and we have these things. So on my product side, as long as this is something that actually happened, there should be one thing that's solid. So again, by the very fact that we're saying this is a solid, we're saying it doesn't do this ionizing stuff. And so you could write, I guess maybe we'll write it this way, 2AgCl, just to show we're making two of those. And then we got the calcium, which is 2 plus, and we've got these nitrates. Now, if you want to write the complete ionic equation, be my guest. I don't think there's any things on this test that actually ask you to write the complete ionic equation. I personally would rather just jump right to the net. And the way you do that is you could just look. It's going to be these. These are my spectator ions here. These are the ones that didn't do anything, and I can kind of just cross them off. And if you look at what's left, Again, I'm not writing a subscript 2. Your net equation should be balanced like any other one, but if you start with a balanced equation and carry everything through, it will be balanced in the end. So I'm not writing a subscript 2 because this is not the element. This is not elemental chlorine. It's chloride ions. Big difference. The element chlorine kills us. This stuff is fine. Now, if you wanted to, it doesn't matter. I wouldn't count it wrong or anything. You actually could reduce this like so, but questions about that?